Imagine waking up, stepping outside, and finding yourself standing where your neighbor's front yard used to be. The wind still whispers through the trees, except now those trees are blackened, lifeless columns. The house that once stood beside them is gone, reduced to a mound of gray ash. The car in the driveway has become a twisted skeleton of melted metal. Half a mile down the road, pieces of another neighbor's roof are wrapped around a telephone pole like soggy cardboard. Then you turn around, and there, standing almost impossibly, is the only structure left intact on the entire street. A smooth, white concrete dome. The windows are still whole. There isn't a single visible structural crack. The front door remains latched, untouched by the inferno and the violent winds that destroyed everything around it. Inside, a family is making coffee, watching steam drift upward through the morning light. For them, this isn't some post-apocalyptic miracle. It's simply Tuesday. That dome required roughly $500 in raw building materials per occupant. The wooden homes surrounding it, the ones that disappeared in minutes, cost more than $200,000 each. And this isn't a hypothetical story. It has happened. From the Pensacola Beach dome that remained standing while Hurricane Ivan tore conventional houses apart around it, to monolithic concrete domes surviving EF5 tornadoes and wildfires powerful enough to turn entire neighborhoods into ash, physics has already demonstrated which shape has the advantage. So why aren't we all living inside structures like this? Why is a home that a family can build in about 1 week for a fraction of the cost of a conventional house practically impossible to build in many suburban neighborhoods? The answer isn't that the material is dangerous. The truth is far more uncomfortable. The modern housing system was simply never designed around something this inexpensive, this efficient, and this independent. Today, we're opening the archive on a remarkable material called Aircrete. We'll explore the surprisingly simple backyard chemistry that can turn cement and dish soap into a fire-resistant fortress. We'll walk through the construction process day by day and see how a dome can rise in just 7 days. And then we'll examine the quiet, bureaucratic machinery that keeps millions of people tied to 30-year mortgages. Grab a cup of coffee. Let's get into it. Part 1. The chemistry of a bubble. What if I told you the secret behind the ultimate disaster-resistant home isn't advanced carbon fiber or military-grade steel? It's soap bubbles. In 2014, engineer and designer Hajar Gibran coined the term Aircrete. But beneath the name, there's nothing rare, classified, or dependent on some billion-dollar patented technology. Aircrete is a remarkably simple, lightweight masonry material made from 3 basic ingredients you can find at an ordinary hardware store: Portland cement, water, and water-based foam. Yes, soap foam. The same basic kind of lather produced by a good-quality degreasing dish detergent. The process feels almost like alchemy. You begin with a specialized device called a foam generator. Gibran created a compact version known as the Little Dragon, designed to sit directly on top of a 5-gallon bucket. The generator agitates a mixture of soap and water using compressed air, producing a foam with a very specific density, ideally around 90 to 100 grams per liter. The finished foam is thick, stable, and surprisingly substantial, almost like heavy shaving cream. Then you fold that foam into a wet Portland cement slurry. And this is where things become interesting. The bubbles don't simply disappear during mixing. They survive the process and become permanently trapped inside the cement as it cures. When the material hardens, you're left with a block, or monolithic wall, containing millions of microscopic, closed-cell air pockets. Those tiny bubbles fundamentally change the physical behavior of the concrete. A typical cinder block weighs around 38 pounds and has a density of roughly 63 pounds per cubic foot. Solid concrete can reach an exhausting 150 pounds per cubic foot. Aircrete is completely different. Using the standard Domegaya formula developed for dome construction, its density is only about 22 pounds per cubic foot. It is so lightweight that a block can actually float on water like a piece of driftwood. You can lift a surprisingly large block with one hand. You can cut it using an ordinary woodworking handsaw, carve it with a kitchen spoon, and even drive screws directly into it. But those millions of trapped air pockets accomplish something else. They transform concrete into a powerful insulating material. Air is a poor conductor of heat. By trapping millions of microscopic pockets of motionless air throughout the cement matrix, Aircrete can achieve an R value of roughly 1.8 to 2.2 per inch. Build a wall several inches thick, and those tiny air barriers dramatically interrupt convective heat transfer. The wall begins behaving like a thermal blanket. But why does a structure built from cement and dish soap feel so different from a conventional house? To understand that, we need to move beyond the chemistry and start looking at geometry. Because there's a reason that when you see Aircrete construction online, you so often see one particular shape, the dome. Part 2. The sacred geometry of the curve. Look around the room you're sitting in right now. Chances are you're surrounded by right angles, vertical walls, and flat ceilings. We've spent generations training ourselves to believe that a house is supposed to be a box. But look at the natural world, and something strange becomes obvious. Nature rarely chooses the rectangle. From the curved structure of your own cells to the eggshell sitting in your kitchen, nature repeatedly returns to the sphere. A conventional rectangular house is actually a structural compromise. It depends on a complicated skeleton of studs, joists, rafters, nails, and roof trusses, all working together to support a heavy roof above the walls. Every joint creates another point where forces must be transferred. Every nail, connection, and corner becomes a potential weakness. When hurricane winds strike a conventional house or an earthquake begins moving the ground beneath it, forces concentrate around those connections. Those stresses search for the weakest location, the place where a roof can peel away or a wall can collapse inward. A monolithic dome works differently. It has no corners, and it has almost no joints or seams. Instead, the entire structure behaves like one continuous, self-supporting compression shell. In engineering, two fundamental forces constantly act on physical structures: tension and compression. Ordinary concrete performs extremely well under compression. It can withstand tremendous loads, pressing inward or downward. But concrete performs poorly in tension. Pull it apart or force it to bend too far, and it breaks. The geometry of a dome takes advantage of that strength. A dome uses what is known as a catenary curve. Because of its shape, external loads, whether gravity, several feet of heavy winter snow, or the violent 250-mile-per-hour winds of an EF5 tornado, are directed into compression. Instead of concentrating at one vulnerable joint, those forces flow smoothly along the curved shell and down toward the circular foundation. That geometry is also why a properly engineered dome doesn't require interior load-bearing walls or columns. The inside becomes almost entirely open. Every square foot can become part of the living space. You can create broad open rooms, dramatic 15-foot ceilings, and sweeping arched doorways without depending on a central beam to hold the roof above you. And when that geometry is combined with a lightweight insulating material like Aircrete, the building process changes dramatically. Domegaya workshops have demonstrated that constructing these domes doesn't necessarily require a massive commercial crew, heavy cranes, or decades of professional building experience. In fact, a beautiful dome shell can be cast and assembled in roughly 1 week. So let me show you what those 7 days actually look like. Part 3. The 7-Day Symphony. Sculpting with ordinary hands. If you've ever watched a conventional house being built from the ground up, you already know how long and complicated the process can become. Framing, roofing, sheathing, insulation, drywall, and between those stages comes an entire procession of specialized contractors. Months can pass before the building even begins to feel like a finished home. An Aircrete dome shell bypasses much of that traditional supply chain. It becomes a 7-day symphony. Day 1 is about establishing the root. You pour a simple circular concrete foundation slab with a reinforced ring beam. That circle defines the footprint of the dome that will eventually rise above it. Day 2 almost looks like a magic trick. A heavy-duty balloon-like membrane, known as an airform, is anchored around the circular foundation. Then you connect a high-pressure blower. Over the next few hours, the enormous membrane slowly inflates. It rises from the foundation until the balloon forms the exact three-dimensional shape of the future dome. Days 3 and 4 bring the heaviest work, but the material itself keeps that work surprisingly light. Instead of lifting heavy masonry blocks all day, a small DIY crew begins producing batch after batch of fresh Aircrete using portable mixers. There are two basic approaches. You can pour the liquid Aircrete into lightweight molds and allow it to cure overnight into custom blocks. Or you can spray and trowel the wet, foamy mixture directly onto the inflated airform, gradually building the shell in thin layers. Because Aircrete contains so much trapped air, enormous volumes of material weigh far less than conventional concrete. That means a crew of only 3 or 4 friends can move a tremendous amount of building material in a single day without completely exhausting themselves. By the end of day 4, the structure has become a continuous, enclosed shell. Day 5 is when construction starts feeling more like sculpture. Cured Aircrete has a density much closer to wood than ordinary concrete, so you don't need enormous industrial concrete saws to shape it. An ordinary handsaw, a chisel, or even something as simple as a kitchen spoon can be used to carve the material. You can literally sculpt arched doorways into the standing structure. You can cut circular openings for windows. You can create skylights. And you can carve narrow channels directly into the walls for metal electrical conduit and plumbing sleeves. Days 6 and 7 are about wrapping and protecting the structure. Aircrete by itself is highly porous and has relatively low tensile strength. Gibran's solution was inspired by the way surfboards are constructed. The interior and exterior surfaces of the dome are wrapped in reinforcing fabric mesh, such as fiberglass or basalt fiber, and then covered with protective waterproof plaster or stucco. This composite system is one of the central secrets of the design. Think about a surfboard. Its foam core alone is fragile. But once that lightweight core is wrapped in fiberglass, the combined structure becomes dramatically stronger. The same principle applies here. The Aircrete forms the lightweight core, while the surrounding reinforcing fabric helps create a high-tensile, highly durable composite shell. On day 7, the balloon is finally deflated. It collapses inward and can be removed through the front doorway. What remains is a hollow, monolithic dome. No traditional wood framing, no drywall, no conventional roof shingles, just a continuous curved shell built by ordinary hands in roughly 1 week, using equipment and materials that can cost less than the down payment on a typical starter home. Which brings us to the numbers. What does an invoice-free home actually cost? Part 4. The invoice-free home. The economics of self-sufficiency. Let's do some honest math. The median home price in America recently passed an astonishing $400,000. For millions of people, buying that house means committing 30 years of their lives to a bank, working 40 hours every week, while a large portion of their income disappears into the interest payments on a box built largely from lumber and drywall. But what happens if lumber and drywall disappear from the equation? According to published estimates from Domegaya, the raw materials required to construct the structural shell of a 1,000 square foot Aircrete dome can cost around $4,000. $4,000. Even after adding the concrete foundation, proper plumbing, electrical work, custom windows, and finished interior plaster, owner-builders have completed elegant, fully functional, multi-dome homes for less than $32,000. In Palawan, in the Philippines, Gibran and his team constructed low-cost Aircrete domes where the core materials cost less than $1,000. Think about what the difference between those numbers represents. It isn't just money. It can represent the difference between decades of financial pressure and a life built around genuine self-sufficiency. And the savings don't necessarily end when construction is finished. They continue throughout the life of the building. The combination of a monolithic dome and Aircrete's insulating thermal mass can dramatically reduce energy demands. Fiberglass insulation can resist heat transfer, but it cannot store thermal energy. Ordinary concrete stores heat extremely well, but it also conducts that heat. Aircrete combines both behaviors. The millions of microscopic air pockets slow heat transfer, while the cement matrix absorbs thermal energy and releases it gradually. The monolithic structure adds another advantage. There are almost no joints or thermal bridges. In a conventional wall, wooden studs can act as thermal pathways, allowing heat to move through sections of the insulated wall. A continuous aircrete shell eliminates those repeated interruptions, helping the indoor temperature remain extremely stable. In Arkansas, builders documented a Domegaya-designed dome remaining comfortably cool during 95-degree summer weather, with 80% humidity, even after the air conditioning had been turned off for hours. During winter, many dome owners report heating large interior spaces using only a small space heater or a compact wood stove. Then there is maintenance. No wood framing means no wood rot. No shingles means no paying a roofing company thousands of dollars to replace a roof after a serious hailstorm. No HVAC service contracts. No endless chain of recurring maintenance expenses. And most importantly, no 30-year mortgage tying you to a job you may not even love. This is the idea of the invoice-free home, a structure designed to demand almost nothing from the utility company, the bank, or the insurance industry. Which raises an obvious question. If a house can really be this affordable and this energy efficient, why isn't this kind of construction everywhere? Why do so many people who attempt to build one suddenly find themselves facing a wall of legal resistance? Part 5. Surviving the Inferno. Nature's ultimate shield. Before we examine the legal obstacles, we need to answer the question skeptics almost always ask first. Is it actually safe? Can something made from cement and soap bubbles really survive a serious disaster? Start with one of the elements homeowners fear most: fire. A conventional stick-built home is, quite literally, a carefully engineered collection of combustible materials hidden behind a relatively thin layer of drywall. There is wood framing, paper-faced insulation, vinyl siding, plastic vapor barriers. Once flames move behind the drywall, the hollow spaces between wooden studs can behave like miniature chimneys. They pull in oxygen, collect embers, and allow flames to travel rapidly upward from one floor toward the attic. A fire that begins in one area can spread through those hidden cavities and consume the structure from the inside out within minutes. Aircrete is entirely inorganic. It is essentially a hydrated network of calcium silicate minerals. There is nothing inside an aircrete wall for flames to consume. No structural wood, no paper, no toxic plastics. Expose aircrete to direct flames approaching 1,200 degrees Celsius, more than 2,000 degrees Fahrenheit, and the material does not burn, decompose, or lose its structural integrity. It does not release toxic fumes, and because the wall is solid and monolithic, there are no empty stud cavities hidden inside it. There is no internal chimney effect carrying the fire upward. There are no attic vents waiting for airborne embers. A wildfire can move directly across an aircrete dome, scorch the exterior stucco layer, and continue past while the family remains protected inside, breathing clean air. Then there are moisture, insects, and mold. In humid climates, conventional wood-framed houses are constantly fighting the natural environment. Termites can quietly eat through structural pine studs from the inside, weakening a house long before the damage becomes visible. Moist wood and drywall can become colonized by rot fungi and mold, releasing spores into the air inside the home. When pests encounter an aircrete wall, they encounter solid cement. Termites cannot eat it. Carpenter ants cannot nest inside it. It doesn't rot or decay. And without organic fibers or paper surfaces providing food, mold cannot establish the same foothold it finds in conventional construction. This is a structure designed to withstand earthquakes reaching magnitude 8 on the Richter scale, Category 5 cyclonic winds, and extreme fires. FEMA has recognized the monolithic dome as providing near-absolute protection. So if science, engineering, and federal agencies agree that this geometry and construction approach can be safer and less expensive than the conventional alternative, another question becomes impossible to ignore. Why can't you simply build one in your hometown? Why does a local planning department sometimes treat an Aircrete dome as though it were the dangerous option? Part 6. The Permitting Limbo, the Machine, and the Prescriptive Path. Walk into your local building department carrying plans for an Aircrete dome, and there's a good chance you'll be greeted with a blank stare, a long sigh, and eventually a rejection. Not necessarily because someone has proven the design unsafe, but because the official behind the counter has a checklist, and your house isn't on it. Most residential construction across the United States, along with much of the developed world, is governed by standards such as the International Residential Code, or IRC. The IRC is largely built around what engineers describe as prescriptive paths. Think of a prescriptive building code as a cookbook. It tells you that if you use a certain grade of 2x4 lumber, space those studs 16 inches apart, use specified nails, and connect the wall to the foundation in a prescribed way, the resulting structure is legally considered acceptable. The inspector doesn't need to perform complicated structural calculations. They can pull out a tape measure, confirm the spacing, check the required connections, and approve the work. Open the IRC, and you'll find 4 familiar structural materials: poured concrete, dimensional lumber, masonry block, and light-gauge steel framing. But Aircrete, non-autoclaved foamed concrete mixed on-site using dish soap, is absent. And once your material falls outside the prescribed list, your project enters a very different part of the system. Section R104.11, Alternative Materials. This section allows a building official to approve an alternative material, but the burden of proving that material falls on you, the homeowner. Now you must demonstrate that your backyard mixture of cement and soap foam is equivalent in strength, durability, and fire resistance to standardized factory-tested building materials. Doing that legally can require an official evaluation report. And obtaining one means paying accredited laboratories to crush samples, expose them to fire, stress them under controlled conditions, and document their performance according to strict testing procedures. That process can cost tens of thousands of dollars. It is a system built for enormous material manufacturers with enormous budgets. Not necessarily for a family trying to build an inexpensive house behind their own home. If you can't afford a $50,000 testing program, the alternative is usually finding a licensed structural engineer willing to evaluate the specific building, perform the calculations, and place a professional stamp on the plans. By doing that, the engineer assumes serious legal responsibility if the structure fails. But Aircrete is still unconventional. Many engineers simply have no experience working with it. Others may be prevented by professional insurance policies from accepting that kind of unfamiliar liability. So the default answer becomes simple: no. The permit department stops the project not because it has demonstrated that your dome is dangerous, but because approving something outside the established model creates uncertainty and liability. But is all of this simply ordinary bureaucratic caution? Or is something deeper helping keep the construction system permanently centered around lumber, drywall, and conventional housing? To answer that, we have to follow the money. Part 7. Follow the money, the lobby, and the financial machine. There's an old rule in public policy. When a system appears completely illogical, stop staring at the logic and start following the money. Maybe the real question was never simply, does Aircrete work? Maybe the question is, who benefits when it doesn't? Start with the influence surrounding building codes. The American timber industry is represented by organizations such as the American Wood Council. These organizations employ full-time professionals whose year-round responsibility includes participating in building code committees and protecting the position of dimensional wood construction within those standards. The concrete bubble dome movement has no comparable army of professional lobbyists. But materials are only one part of the story. Think about the financial ecosystem surrounding an ordinary house. When someone buys a $400,000 home, that money doesn't simply pay for lumber. The house generates revenue for an entire network of industries. A bank can earn hundreds of thousands of dollars in interest over the life of a 30-year mortgage. Utility companies collect payments every month because conventional stick-frame construction can lose heat through the structure, including wooden studs that interrupt the insulation layer. HVAC companies depend on heating and cooling systems that eventually wear out and need repair or replacement because the building itself requires active mechanical climate control. Pest control companies return year after year. Roofing contractors replace damaged shingles. Drywall installers repair damaged interiors. Entire businesses operate around the weaknesses and maintenance requirements of conventional wood and drywall construction. Now imagine a house that uses thermal mass to regulate temperature, geometry to improve efficiency, cement to resist termites, and costs only $30,000 to construct. That kind of house asks far less from the system. It produces fewer recurring invoices, and even if you manage to secure a building permit, the financial machine can create another barrier. Call a bank and ask for a construction loan for a dome. There's a good chance the answer will be no. Banks rely heavily on appraisals based on comparable sales. In other words, they want to see similar homes that have sold nearby during the previous year. But what happens when you're building the first Aircrete dome in your county? There are no comparable sales. There are no comps. According to the logic of the spreadsheet, your highly efficient, fire-resistant home can suddenly appear to have no measurable market value at all. Then call an insurance company. Without standardized actuarial tables for Aircrete homes, the insurer may refuse coverage or demand an enormous premium, regardless of the structure's resistance to fire and extreme winds. The result is a self-reinforcing machine. The code official follows the prescriptive path. The appraiser follows comparable sales. The bank follows lending criteria. The insurance company follows actuarial tables. And every part of the system pushes toward the same result. Standardized, expensive, fragile boxes. But this is where the story becomes interesting. Because the machine has edges. And right now, a growing community of unconventional builders is learning exactly how to work around those edges and build these homes legally. Part 8. Cracking the code. The rebels building on the edges. So how are people doing it? How are builders actually creating Aircrete homes legally today? They're learning to use the system's own rules. The first path is what we could call the engineering translation. You don't walk into a permit office and describe your project as a DIY soap bubble dome. That immediately sounds unconventional. Instead, pioneering groups such as Domagaya have worked with licensed structural engineering companies, including PSE consulting engineers, that understand alternative materials. They translate the organic dome into professional engineering language. Suddenly, the structure isn't a homemade bubble house. It becomes a fiber-reinforced, non-autoclaved, foamed concrete thin-shell compression structure. That language matters. When you arrive at the plan check desk, carrying engineering drawings officially stamped by a licensed structural engineer registered in your state, the building department now has something it desperately needs: a legal shield. The engineer accepts professional responsibility for the structural calculations. The inspector can evaluate the plans and approve the alternative material pathway with far more confidence. This is essentially how Catherine Wilde accomplished something many people believed was impossible. In the rainforest of Queensland, Australia, she built Elysian Falls, a remarkable 90-square-meter multi-dome Aircrete home. She spent years battling paperwork and thousands of dollars navigating the approval system, but ultimately became the first person in the world to receive complete official council approval and engineering sign-off for a multi-dome Aircrete residence. Today, her architectural plans are available online. They provide future builders with something extremely valuable: an example showing local officials that an engineered, legally approved Aircrete dome already exists. The second path is the legal buffer zone. Across many counties and states, small structures beneath a certain floor area, often around 200 square feet, can be built without a building permit. That is where a huge part of the Aircrete community begins. Small guest cabins, off-grid studios, workshops, emergency shelters. By beginning with a smaller project, builders can learn how to operate foam generators, refine their mixture ratios, and develop practical experience using Aircrete in their own climate without immediately entering the permit process. The third strategy is finding permit-friendly havens. There are still large regions where traditional prescriptive building enforcement has very little reach. Cochise County, Arizona, for example, offers an owner-builder amendment that allows people to construct almost anything they want with no inspections, provided they build it for themselves and live there. Some unincorporated areas of West Texas have no active residential building code enforcement. Greenlee County in Arizona, along with certain rural counties in Colorado and Missouri, can have minimal building regulations. In places like these, people can build homes shaped more by imagination than convention. They can combine the ancient physics of curved structures with the modern chemistry of Aircrete and pursue something increasingly rare, a home designed around freedom from debt and utility bills. The choice of curves. For thousands of years, human beings lived inside curves. From Arctic igloos to the mud domes of Africa, our ancestors built structures that worked with the earth. They used local materials and natural geometry to create shelters that were resilient, efficient, and emotionally welcoming. The box came later. As construction became industrialized, straight walls became easier to standardize. Timber could be stacked efficiently. Copper pipes could run in straight lines. Square sheets of drywall could roll off factories and cover rectangular rooms. But as we prioritized what was convenient for the factory, we sacrificed some of what made the shelter resilient. We traded structures capable of facing fire and violent storms for boxes of combustible material that could also tie families to 30 years of financial obligation. Aircrete domes represent a quiet revolution against that model. The technology exists today. Using ordinary cement and household dish soap, people of ordinary means can gain the ability to build something extraordinary with their own hands. It represents a different relationship with shelter. Instead of viewing a house as a permanent financial liability, the home can become what shelter was always meant to be: a sanctuary, something that protects you, something that supports you. The physical technology is already here. The chemistry works. The geometry is ancient. What remains in the way is the paperwork. But every time a builder like Catherine Wild pushes through that paperwork and receives approval, another crack appears in the prescriptive system. Every time a family builds a small, permit-free Aircrete dome in the backyard, another group of people learns what is possible. Case by case, the paperwork is beginning to catch up. So look around the house you're sitting in right now. Look at the straight walls, the utility bills, the mortgage, and ask yourself one liberating question. Are you willing to remain inside the box, or is it time to start thinking in curves? If you want to be part of this quiet revolution, hit the subscribe button, check the resources in the description below, and tell me in the comments, would you build an Aircrete dome in your backyard? And if you wouldn't, what's holding you back? This is The Roots Survived. Thanks for watching, and I'll see you in the next build.